Up until now in AGEC 350, we've basically assumed that benefits and costs are known, that if you do a project, you're going to get so much benefits with certainty, or you're going to pay the costs with certainty. But of course, in reality, benefits and costs are usually uncertain. So let's consider an example of how we might deal with this uncertainty. So suppose that we've estimated that the willingness to pay of the public at large is $3 million to protect some bird. And we were considering a policy that will have a 70% chance of success and a 30% chance of failure. That is, 70% of the time we expect that the bird will be saved, but 30% of the time this project is not going to work and the bird will not be protected and will lose that species. So in this case, we would estimate an expected willingness to pay of 0.7 times 3 million plus 0.3 times 0, or what you get if you don't save the bird, yielding an average or expected value of $2.1 million. In general, that's all we do. We use expected benefits and expected costs to carry out benefit cost analysis and to evaluate the efficient level of an environmental service. That should be all easily understood, and you can easily see how you might extend the normal approaches that we've been using over time to a case where there's some statistical uncertainty about the outcomes of a project. But what if we're talking about human lives, where much of what we do is very risky, and we really don't know whether you're going to save any particular life or not? Can we do anything in this situation? And the economist's answer is emphatically yes. And the approach that is used by economists is what's called the value of a statistical life. So let's take an example. Suppose that I'd be willing to pay $600 for anti-lock brakes on my car. That is, in addition to the cost for the standard car, there's a $600 extra fee for anti-lock brakes, and I'm willing to pay that. I know that anti-lock brakes reduce the chance of my dying from 3 in 10,000, or 0.0003, to 2 in 10,000, to 0.002. So I'm getting an improvement, a slight reduction in the risk that I'll die from a car crash. An improvement of exactly 0.001. Now, what this means is that for every 10,000 people that buy anti-lock brake, one life on average will be saved. How much do those people spend for those anti-lock brakes? Well, for every 10,000 people that buy anti-lock brakes, one life is saved. Those 10,000 people would spend 10,000 times 600, or $6 million to save, on average, one life. So we call this approach that we have collectively demonstrated a value of a statistical life of $6 million. Now, notice this is not a revealed or a solicited preference or a approach. It's a revealed approach. We're actually using market behavior to determine what the value society places on a statistical life. The general approach for measuring a value of a statistical life can be shown in this formula here. So we've got three terms here. The value of statistical life is equal to V, which is what you're willing to pay for a change in the probability of risk, and delta R is the change in mortality. You simply divide V by delta R and you get your value of statistical life. So in my case, I came up with a willingness to pay of $600. I divided that by 0.0001, and that gives me $6 million. On the cost side, we can do exactly the same thing. We can find the cost per statistical life, that is, what it would cost society to save a life, is simply going to be equal to the cost of changing the mortality risk divided by the change in probabilities. And this can actually lead to some pretty revealing numbers. Viscusi, these are pretty old numbers now, they're from 1996 review paper that he did, and he sort of looked at the cost of statistical life for a bunch of policies, and you'll see that, so for example, there are regulations on unvented space heaters to prevent fires. That annually saves $50, or 50 lives, at a cost of only $130,000 per year, so that's a pretty cost-effective policy. Seat belts cost a fair amount. They save 1,800 lives a year, a cost per life of $390,000. At the other end of things, you've got asbestos policies, which actually save a lot of life, but they're very expensive. So we're seeing a reduction or a cost per life of $115 million saved for those asbestos regulations. Formaldehyde is another extreme case where we've got regulations. Maybe the cost of those regulations is not so onerous, but we're hardly saving any lives. On average, only 1/100th of a life is saved every year in the United States, which leads us to a cost per statistical life of $92 billion. So a lot of the policies that are used in the real world actually have a wide range of cost per statistical life. So in general, we can think about using a value per statistical life, and the value that is normally used ranges between 3 million and 8 million. I think an average value used these days is around $6 million per statistical life, and that's actually used in policy making. The problem is that there's some really serious concerns with this approach, and that is that people don't behave rationally. A lot of times you'll see people spending a lot of money on things that aren't going to save their life, and they're ignoring or don't spend money on things that would save their lives. So we have to be somewhat cautious in applying the value of statistical life approach to dealing with real-world problems. Nonetheless, it is certainly a helpful economic lens in which to view these policy challenges. So that's my lecture on risk under uncertainty. It'll be helpful in understanding some of the material in the textbook. That's the end.